Thank you for watching this video. My name is Florian Lonsing. I will present our paper, A Theoretical Framework for Symbolic Quick Error Detection, that was published at FMCAT 2020. This is joint work with Subhashish Mitra and Clark Barrett from Stanford University. The context of our work is pre-silicon verification of processor designs. Pre-silicon verification is an important step in electronic design automation as it allows us to catch logical errors in a design before fabrication. We are interested in applying model checking for pre-silicon verification. Model checking is a formal technique where we formally verify a model of the design given as a Verilog implementation, for example. Model checking is in sharp contrast to traditional non-formal techniques like simulation or testing. In our work, we consider the soundness and completeness of the model checking workflow in terms of bug finding. Let's have a look at soundness first. Consider a model M of a design where a certain number of bugs and a set of properties that define the formal specification. A model checking workflow is sound if for every property that does not hold there exists a bug in the design. In other words, a sound model checking workflow does not produce spurious counterexamples. We say that the property P that fails covers a particular bug. For a model checking workflow to be complete, we require that for every bug in the design, there exists a property in the specification that fails. Completeness means that the specification, that is the set of properties, covers all bugs in the design. We can detect every bug by checking a property that will fail. It has been a long-standing challenge to check whether a specification is complete. For instance, a related paper was published at CHARM more than 20 years ago with the descriptive title, "Have I written enough properties?" That is indeed the main point. How do we know that the set of properties in the specification covers all bugs in the design? That is a difficult problem in practice because we have to write properties manually, and these properties are specific to the given design implementation. Moreover, if the design changes, then we have to adapt the set of properties manually, which is error-prone. To conclude, the completeness of bug finding in model checking depends on the set of properties, that is, the specification that we are checking. To address this challenge, we consider symbolic quick error detection, or SQED. SQED is a model checking technique based on bounded model checking. In contrast to traditional model checking, SQED does not require implementation-specific properties or a full formal design specification. Instead, SQED checks whether a design is self-consistent, that is, whether it produces the same outputs whenever we provide it with the same inputs. Self-consistency is a universal property. That means it is implementation independent. We can easily swap out the original design M and instead check another design M' without having to manually adapt a set of properties. It was shown that SQED is effective in practice on commercial designs in terms of bug finding capabilities. In industrial case studies, for example, SQED detected all bugs that were detected by traditional verification techniques like simulation or testing. SQED also detected additional bugs that were missed by these techniques. However, there has been no formal characterization of the bug finding capabilities of SQED. In our work, we make significant progress in that direction. First, we prove that SQED is a sound technique. It does not produce spurious counterexamples when it reports that the design is not self-consistent. Second, we explore conditions under which SQED is complete. Ultimately, we prove that SQED is fully complete and covers all bugs with respect to the unrolling depth of BMC. Here, we define bugs in a general and natural way within a formal framework that we use to model processor designs and SQED. Before we go into the details of our results, let's take a look at the basic principle of self-consistency. Consider a function f. In a mathematical sense, we expect from function f that it produces the same output whenever it is provided with the same input. This property is expressed by the following well-known functional congruence axiom. For all x and x prime, if x is equal to x prime, then f of x must be equal to f of x prime. With SQED, we apply this principle of self-consistency to processor designs. If we run the same instruction sequences and inputs on the processor, then we expect the processor to produce the same outputs. Here, the inputs of an instruction and its outputs are defined in terms of the values stored at particular register and memory locations. Note that running a processor on the same instructions and inputs does not mean that the processor is in the same state at the time of execution. In particular, hardware designs like processors have a complex internal state due to pipeline implementations, for example. It is that complex state that causes bugs that are hard to find in practice. Next, we define formally what it means to run the same instruction sequence twice and how the inputs to the instructions are defined. In our formal framework, we represent a state of a processor, like S0 shown above, as a mapping from a set of locations L to values. A state consists of an architectural and a non-architectural part. The architectural part, denoted by SA, represents the mapping from locations to values and can be updated explicitly by executing instructions. The non-architectural part, denoted by SNA, is updated only implicitly and represents control information like pipeline registers. In our model, however, we abstract away complex details like instruction pipelines. The set of locations is an abstraction of register and memory locations. An instruction I consists of an opcode, an output location, and two input locations. Executing instruction I in state S0 produces a successor state S1 in one step, where we both update the architectural and the non-architectural state part of the state. The self-consistency property that is checked in SQED is based on a partition of the set of locations L into original and duplicate locations, denoted by LO and LD. Given the partition, we define an arbitrary but fixed bijective mapping LD between the sets of original and duplicate locations. Referring to the example, given a set of 32 register identifiers, we can partition that set into a set of original identifiers 0 to 15 and duplicate identifiers 16 to 31. We can define the bijective mapping LD by adding the value 16 to a given original location L. For self-consistency checking, we do not run the same instruction sequence twice, but two versions of the same instruction sequence, an original and a duplicate version. The duplicate instruction has the same opcode as its corresponding original one, but operates on duplicate locations. Continuing our example from before, consider an original add instruction that adds two values at locations L4 and L8 and writes the result to location L12. Using the mapping LD, we generate a duplicate instruction by keeping the opcode, but mapping the input and output locations to their corresponding duplicate ones. When executing instructions, an original instruction modifies only original locations and duplicate instructions modify only duplicate ones. In the picture above, this is indicated by the change of the white boxes to gray boxes. In order to compare inputs and outputs of instructions, we define the concept of QED consistency. A state S0 is QED consistent if and only if, in S0, all original locations have the same value as their corresponding duplicate ones. In our example above, if state S0 is QED consistent and the original instruction IO executes correctly, then the duplicate instruction ID will get the same input values in state S1 as the original instruction IO got in state S0. If the duplicate instruction ID executes correctly in state S1, then the final state S2 will be QED consistent. We extend the notion of QED consistency of states to the execution of sequences of instructions. A QED test I is a concatenation of a sequence of n original instructions and a sequence of n corresponding duplicate ones. If we execute the two n instructions of a QED test in a QED consistent initial state S0, then we obtain a QED consistent final state S21. However, note that QED consistency is preserved by the instructions in a QED test only if all instructions execute correctly. SQED applies bounded model checking to systematically and exhaustively generate QED tests as follows. Given a design we want to check, we first partition the set of locations and define a bijective mapping LD between original and duplicate locations, as in the example that we have seen before. Then we select n original instructions, where we start with one original instruction. Given the n original instructions, we generate n corresponding duplicate ones using the mapping LD that we have chosen. By concatenating the original and duplicate instructions, we obtain a QED test I, which we execute symbolically on the model of our design. We start execution in a QED consistent initial state S0. Executing the QED test produces a final state S2n. If the final state is not QED consistent, then the QED test constitutes a counterexample to self-consistency. Otherwise, if the final state is QED consistent, we have to decide whether to continue using the partition and mapping that we have chosen. If not, we start over with a new partition and mapping. Otherwise, we increase the number n of original and duplicate instructions and continue generating QED tests. In existing SQED implementations, a fixed partition and mapping is chosen once at the start. In order to formalize the correctness of instruction execution, we define an abstract specification relation. The abstract specification expresses general and natural properties that we expect from correct executions of instructions. Let I be an instruction that is executed in a state S and results in a successor state S prime. Instruction I executes according to the specification if and only if, first, all non-output locations remain unchanged, and second, the instruction produces the correct output value at its output location. It is important to note that we need the abstract specification only in our theoretical framework. For practical applications of SQED, no specification is needed. Given the abstract specification that we've just defined, we now define what it means for a processor to be correct. A processor is correct if every instruction I executes correctly in every reachable state. A bug is a counterexample to correctness. It is defined by an instruction IB and a set SB of bug triggering states. Every bug triggering state S is reachable, and the bug instruction IB fails to execute according to the specification in that bug triggering state S. Given these definitions, in order to trigger a bug, we must execute a setup sequence of instructions. The setup sequence starts in an initial state and reaches some bug triggering state S in the set SB. The bug instruction IB fails to execute according to the specification in the state S. As special cases of bugs and instruction correctness, we define single instruction bugs and single instruction correctness. A processor P is single instruction correct if and only if all instructions execute correctly in all initial states of P. A single instruction bug is an instruction that executes incorrectly in at least one initial state. Unlike the bugs we defined previously, single instruction bugs do not require a setup sequence. They are well studied and easier to check than general bugs since we can focus on the initial states of the system. Checking single instruction correctness is complementary to SQED because QED tests cannot detect every single instruction bug in general. Hence, in the following, we assume that the processor P is single instruction correct. As one of our main results, we prove the soundness of SQED. Given a QED test I and a QED consistent initial state S0 of some processor P, we say that QED test I fails if the final state S that results from executing I starting in state S0 is not QED consistent. The main soundness theorem states that if there exists a failing QED test for processor P, then P has a bug with respect to some abstract specification relation. Soundness shows that every failing QED test corresponds to a bug in the processor that is a violation of the abstract specification relation that we have defined. In order to prove completeness of SQED, we must show that we can construct a failing QED test for every bug in a processor P. We call such a QED test a bug-specific QED test, which must have the following properties. Starting in a QED consistent initial state S0, we execute the QED test, which consists of n original and n duplicate instructions. We assume full flexibility in choosing the mapping LD. We choose the first duplicate instruction ID1 to be the bug instruction IB. At the same time, IB is the duplicate of the first original instruction IO1. Since IO1 executes in an initial state, we know that it executes correctly due to single instruction correctness. The sequence of original instructions in the QED test is the setup sequence required to reach a bug triggering state, that is state Sn in our example. The bug instruction IB, which is the first duplicate in the QED test, fails in state Sn. For this example, suppose that the bug instruction produces an incorrect output value at its output location L in state Sn plus 1. We know by single instruction correctness that the first instruction, IO1, has produced a correct value at its output location L' in state S1. Therefore, the values at locations L and L' mismatch and must propagate all the way to the final state S2n. Consequently, the final state S2n is QED inconsistent and hence the QED test fails, which will be detected by SQED. Given a bug-specific QED test, we obtain the following conditional completeness result. If a bug-specific QED test I exists for a particular bug in a processor, then that QED test I fails. This completeness result is conditional on the existence of such a QED test. There are known classes of bugs for which no bug-specific QED test exists, however. For example, bugs in the forwarding logic of a pipeline processor. We address these classes of bugs next to ultimately obtain full completeness of SQED. To obtain full completeness, we consider extensions of QED tests. For these extensions, we assume that the instruction set architecture of the processor has special reset instructions. A soft reset instruction makes a transition back to an initial state S' while keeping the architectural part of the state S where it is executed unchanged. That is, a soft reset instruction does not change the values stored at the locations in a state. A hard reset instruction can make a transition to any arbitrary initial state S', that is, it has full flexibility to also change the architectural part. Given hard and soft reset instructions, we now define QED tests with reset. This extension results in a variant of SQED that is fully complete. Suppose that a bug in the processor is set up and triggered by the instruction sequence I1 up to IK, with IK being the bug instruction that fails. In contrast to QED tests we defined previously, when running a QED test with reset, we do not duplicate instructions and do not check QED consistency. Instead, we run the same sequence twice with reset instructions inserted. Then we directly compare the states of the processor. First, we execute the setup sequence from an initial state Si to trigger the bug. The bug instruction fails and produces a wrong value in state S. Then we execute a hard reset to go back to exactly the same initial state Si where we started from. The idea is to execute the same instruction sequence again, but execute a soft reset before executing the bug instruction IB. Executing a soft reset results in an initial state. Now we can make use of the fact that the processor is single instruction correct. We execute the bug instruction IB in that initial state, due to which it will execute correctly and produce a correct result in state S'. Finally, we compare S and S'. These states resulted from the bug instruction with and without executing a soft reset before. Instead of QED consistency, we check whether S and S' have the same architectural state, that is, whether the values at all locations match. If this is not the case, then the QED test with reset failed. This leads us to our main result on full completeness. If a processor is single instruction correct and has no failing QED test with reset, then it is correct. For practical applications of SQED using this theorem, we would explore all QED tests with reset up to the considered BMC bound. Let's summarize our main results. SQED is a model checking technique that checks whether a model of a processor design is self-consistent. The self-consistency check amounts to checking whether the design produces the same outputs whenever it is provided with the same inputs. We proved that SQED is a sound technique. Soundness means that whenever SQED reports that the design is not self-consistent for particular inputs, then there exists a bug in the design. In other words, SQED does not produce spurious counterexamples to self-consistency. We also explored conditions under which SQED is complete and ultimately obtained a variant of SQED based on reset instructions that is fully complete. Completeness means that whenever there is a bug in the design, then there exists a self-consistency check that can be carried out by SQED that fails. In order to prove our theoretical results, we defined a formal framework to reason about processor designs and applications of SQED. In our framework, we define processor correctness and bugs in terms of an abstract specification. That abstract specification is needed only in theory to formally characterize instruction failure. In practice, no formal specification is needed to apply SQED. As future work, it would be interesting to leverage our theoretical insights in practical implementations of SQED. Existing implementations do not yet generate QED tests with reset instructions, on which our full completeness result is based. Support for reset instructions could be explored in a design for verification approach, where the instruction set architecture of a processor provides reset instructions natively. Alternatively, the effect of reset instructions could be implemented on the software side in a model checker. Regarding our formal model of processors and SQED, we want to consider several refinements. In one direction, we want to refine our model to represent more complex design features such as instruction pipelines and multiprocessor systems. In practice, SQED was found effective in the detection of deadlocks. It would be interesting to formally characterize and reason about deadlock detection. Finally, we want to formally reason about variants of SQED that execute QED tests from symbolic starting states rather than from concrete ones. Symbolic starting states allow to overcome the situations where large BMC unrolling depth become prohibitive in practice. This concludes our presentation. Thank you very much for watching this video.